Hello, I'm Alan Bowling in the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. This presentation is part 3 of derivatives and integrals in dynamics. So let's get started. Okay, once again we were looking at the problem of us flying from this point, flying over to this other point, and our friend would be flying from here all the way over through here. And we want to find out the conditions or the velocities that we would have to be flying at to collide right here in the middle if we were flying at the same altitude. So in part 2, we're able to integrate the velocity information up to position information, and assuming that we were going to both fly at a constant speed. So when we did that integration, we ended up with this relationship here, which tells us how our speeds relate to our friend's speeds. And given that 9 over 16 is a number that's less than 1, it's indicating that our speeds are probably going to be larger than our friend's speeds. But we have to go check this out in detail. So let's do that next. Okay, so let's look at our velocities now. So we say dx1, which is our velocity in the north direction, was equal to a. And dy1, which is our velocity in the east direction, was also equal to a. So we know that we can find the magnitude, those are the components in each direction of our velocity. So we can find the overall magnitude of our velocity as, which we can designate magnitude of v1, which is our velocity, is going to be the square root of each of the components added together and taken the square root. So we have a squared plus a squared is going to be the square root of a squared times 2. So we're going to get a times the square root of 2 is the magnitude of our velocity along the path. Now for our friend, it's a little bit more complicated because he had dx2 over time. His velocity was b, and that's equal to 9 over 16 times a. And his y velocity was negative 3/4 dy2. d2 was equal to b, which is equal to 9 over 16 times a. So if you do that, if you work that out, you'll end up with dy2 dt as being equal to minus 4 over 3 times 9 over 16 times a, which now if we cancel things out, we will get 3 minus 3 over 4 times a. So our friend's velocity is going to be, we can find the magnitude of v2 as being equal to the square root of the components of their velocity squared. So it's going to be 9 squared over 16 squared times a squared plus 9 over 16 times a squared, which is not easy to figure out. So that's 9 squared over 16 squared plus 9 over 16. However, if you have a handy-dandy calculator, you'll see that this is equal to a times 0.9375, and you will find that this guy, our velocity is going to be equal to, this is going to be equal a times 1.41. So whatever speed we're moving at, we're going to multiply, we're going to be moving at a times 1.41, and our friend is going to be moving at a times 0.9375. So if you want to see the relationship between the two, you can say, okay, V1, magnitude of V1 over the magnitude of V2 is going to equal A times 1.41 divided by A times 0.9375, and you'll find that that's equal to approximately 1.5. So we're going, so our friend, or our speed, is 1.5 times our friend's speed. And if we do this, we will collide. So the bottom line is, we don't want to travel at that relationship. We don't want our speeds to be related in this way. So we don't want to be flying at 1.5 times faster than our friend. Otherwise, we will collide. So if we go back to the real world, it's telling us that if we fly along this path at 1.5 times the speed that our friend is flying along their path, we're going to collide here in the middle. So we want to just avoid that speed, and if we don't do that, then we won't collide. And that's the answer to the problem. So in summary, we investigated velocity and position to avoid a midair collision. And we found that given the parameters of the problem we set up, and assuming we're flying at a constant velocity, we should not fly 1.5 times faster than our friend if we want to avoid a collision. So thank you for watching.